Section 2.5, free fall acceleration. All right, so taking a look at this, free fall acceleration is defined as the rate an object accelerates downward in the absence of air resistance. It will vary slightly with latitude and elevation, but it's known as g, and the standard value is accepted to be 9.8, exactly 9.8 meters per second squared. So this is a variable that will pop up quite a bit. An interesting thing about free fall acceleration is even though it does have some latitude and elevation dependence, it is independent of the properties of the object itself: mass, density, shape. So the acceleration should be the same regardless of the object. They should accelerate together. That to me says, if I set up a race between, like, say, a sheet of paper and a marker, if I drop these, that they should hit the ground at the same time if they have the same acceleration pulling on them, right? Well, we can test it out. You can test it out at home, right, with your own pen and a piece of paper if you have one. So let's see if it works if we have the same acceleration here. So I'm going to release in 3, 2, 1. I don't know if you could see that all the way. The paper did not fall at the same rate as the marker. Why is that? Well, let's take a closer look. The equations will apply to free fall near Earth's surface. So we're going to look at vertical flight here along the y-axis. So again, a single direction. Even if it's not horizontal, it's still a single direction. And where air resistance can be neglected. As long as you're reasonably close to Earth's surface, you can neglect air resistance. It does have some impact, but it complicates all the calculations. So for now, we're keeping it simple. You can go on and study this in more depth, but air resistance is a key detail here. The free fall acceleration is downward. It's in the negative y direction, negative direction. So in all of those constant acceleration equations, those 5 super equations, the a, you're going to substitute in a value of negative g, or negative 9.8. So this means the free fall acceleration near Earth's surface is a, the acceleration is equal to negative g, or negative 9.8 meters per second squared. The magnitude of the acceleration is given by g, by the positive 9.8. So we don't want to substitute in a negative 9.8 for g. G is always positive. This is something that's subtle but really easy to miss. Now, if we go back to the paper and marker example, right, where I dropped these and they didn't fall at exactly the same rate. Why didn't they fall at the same rate? Well, the key is that this paper had a bunch of air resistance get in the way. Well, what if we could take all the air out of the way of the paper? Would these two then fall at the same rate? It turns out this is something scientists have done and have tested. So they took feathers and a bowling ball and took them to a giant vacuum chamber where they pulled all the air out. And when they did that, boom, they fell exactly the same. You look at the feathers, it looks like they aren't even moving through air, right? Because their orientation looks exactly the same. It's not until they hit the ground that they get disrupted, because there's no air to disrupt their motion. There's a whole video on this. I'd encourage you to check it out. You can watch them go through. It's delightful. I could just watch even just this GIF all day of watching. This shows science works, right? In the absence of air resistance, all objects fall with the exact same acceleration. It's always going to be that negative g, or negative 9.8 meters per second squared. All right, with this in mind, let's take a look at a think pair share with a ball toss. So if you toss a ball straight up, or a marker, whatever you might have, what is the sign of the ball's displacement for the ascent from the release point to the highest point? What is the sign for the descent from the highest point back to the release point? What is the ball's acceleration at the highest point? So these are the questions that I want you to consider. So please go ahead and reflect on this, come up with answers, and pause the video until you do so. All right, did you do that? I'm hoping so. Well, you might have a better chance of tossing than I did with my marker there. That was pretty sad. But let's see. First for A is looking at when we toss the ball straight up. Right? So when it's going straight up, the ball, say, starts somewhere and then goes up and finishes somewhere else. Well, this means we are moving in the positive direction. So it is going to be a positive displacement, right? So positive delta x. What about on the descent? Well, the descent is defined as from the highest point back down to the lowest point. So the ball is moving in the negative direction, and if you take a small number like 0 minus a big number like positive 10, you'll get a negative answer out. So this is a negative displacement, negative delta x. Right. Hopefully you're still on board here. The last one, though, question is looking at the ball's acceleration at the highest point. And this is where it gets really tricky, because at the highest point, the ball stops. It is neither moving up now, nor is it moving down. And so at this highest point, the velocity is briefly 0. So velocity is equal to 0 up there. Does that mean the acceleration must be 0? Because the acceleration is the derivative of velocity with respect to time. It's an interesting thought, right? But we know our acceleration, if something is in free fall, if it's freely moving near Earth's surface, must always be negative g, negative 9.8 meters per second squared. So how can we reconcile this with the fact that the velocity is briefly 0 there? Well, it's only 0 for an instant, and we can't take the derivative of a single instant in time. We need to take the derivative as a function in time. So if our position starts out at 0 and goes up to some point, here we can make a graph here. So position versus time. So it goes up to some point and then it comes back down to 0. That's our position versus time. And if we look at our velocity versus time, I like to think in terms of graphs. Maybe you have another way you like to think about it. We start out with a large positive velocity. It decreases down to 0 at that highest point, right? And then it continues to become more and more negative in velocity. So we finish with a large negative velocity going down. Well, we know acceleration is the derivative of the velocity as a function of time. So if I want to plot the acceleration, notice when I take the derivative of this velocity versus time, it's just a constant. At all points, it has this negative slope. And that negative slope is given by exactly negative 9.8 or negative g. So if we double check the answer, we find that indeed the ball's displacement is positive on the ascent, negative displacement on the descent. The acceleration, though, is always negative 9.8. Anywhere in the trajectory, right? We aren't worrying about the hand tossing it or the fact that it stops when it hits the hand. We're just worried about while it's in the air. So this introduces the idea of free fall acceleration, and we will see plenty of examples of this. We'll also get to do it in 2 dimensions when we get back to it in chapter 4.